In this lesson, we are going to be exploring fractional equations that are a little more complex than we saw in the previous lesson. Fractional equations that are a little more complex and are going to require a tiny bit more thinking as we work our way through them. Hopefully, we're going to try to eliminate the fractions as we begin to solve these equations by clearing the denominator. That's going to require us to find the least common denominator because we'll be dealing with more than one fraction in each of these relationships. Once we've identified the least common denominator, we're going to choose to multiply the entire equation by the LCD. You can multiply an equation by whatever you want, as long as you do it equally on both sides. That is the multiplicative property of equality. And then you can simply solve the multi-step equation that remains after you have gotten rid of the fractions. I'm going to begin with question number 1. And in question number 1, ladies and gentlemen, I'd like to show you how you might have seen this in previous years, either in 7th or 8th grade, depending upon what you took last. So for question number 1, if you wanted to determine the value of x that when you took half of it and added it or increased it by 1/6 of its value, the result would be 2, you might choose to put up a fence. And as you had done in either 7th or 8th grade, you might recall that when you add fractions, or subtract for that matter, you need to have a common denominator. So it would be efficient to try to determine the common denominator of the two fractions in the expression on the left and add them together. You might further recall that the common denominator for 2 and 6 would be 6, or the least common multiple. So you might choose to multiply the first fraction by 3 over 3. 3 divided by 3 is just 1, and anything times 1 is itself. If you chose to multiply 1/2 of x times 3 over 3 and simplified that relationship, you'd end up with 3 times x in the numerator, 3x, and 3 times 2 in the denominator, 6. And then you could increase that by x over 6, or otherwise known as 1x over 6, to equal 2. Once you've gotten your common denominator in the expression on the left, you can simply add those fractions together by adding the numerator and keeping the denominator, leaving you with 4x divided by 6, or 4/6x, equal to 2. There are several ways to approach the relationship or the equation at this point. You might choose to put 2 over 1 and cross multiply, interpret it as a proportion. You might also choose to recognize that since you're working with a fraction, it would be efficient to multiply both expressions by 6, undo division or multiplication. Or you might choose to divide out the coefficient of 4/6 on x. You might say the opposite of multiplying is divided. Once you've done that, you could either divide the expression on the right by 4/6 as well. You could do whatever you want to in an equation as long as you equal on both sides, in this case dividing by 4/6. Or you could recall that division is the same as multiplying by the reciprocal, and you could choose to multiply the expression on the right by 6/4, the reciprocal of 4/6. Having done that, or having presented that, you could then actually perform the simplification. In the expression on the left, 4/6 will divide into itself perfectly one time, leaving you with just 1x. You do not need to write the coefficient of 1. And the expression on the right, technically you have 2 over 1 times 6/4. You're not wrong if you say, if you actually perform 2 times 6 in the numerator and 1 times 4 in the denominator, and you get 12/4, and then you perform that division, and that would be equal to 3. Or you could simply simplify before you multiply. You could say that 2 divides to 4 2 times the denominator and once in the numerator, and you're left with 6 divided by 2, and 6 divided by 2 is simply 3. X should be equal to 3. If you check your work, you can substitute 3 in place of that, substitute using parentheses, and the expression on the left, the result would be 3/2 increased by 3/6 equals 2. You can type that into your calculator to determine the value of the expression on the left. Or you could get a common denominator once again. You could multiply the numerator and denominator by 3 to present this as 9/2 plus 9/6 plus 3/6 to see if it actually equals 2. 9 plus 3 is 12 in the numerator. Add the numerator, keep the denominator. And 12 divided by 6 is in fact 2. Therefore, the answer to the value of x that make the expressions equivalent for question number 1 is x equals 3. I'm going to do that question again. So the workspace for question number 2, I'm just going to recopy question number 1, and I'm going to show you an alternative way to do it that is a little more mathematically efficient, and it's going to allow us to solve some of the more complex equations on the back of the worksheet. If you had originally interpreted this question as this equation as an equation with fractions, and fractions that have denominators, they always do, denominators when we divide, you might say, wouldn't it be efficient to undo the division right away? That way we don't have to work with fractions any longer as we make our way through the equation. Having done that, you'd have to know that the fractions have denominators of both 2 and 6. And you'd want to choose to multiply by a number that 2 and 6 divide into. So the multiples of 6 are 6, 12, 18, and 24. And the multiples of 2 are 2, 4, 6, 8, and so forth. The least common multiple, the smallest amount that both 2 and 6 divide into, is in fact 6. Now you could have multiplied by other amounts that 6 and 2 divide into, like 12, or 18, or 24, and you would get the same result. It just might be a little more complex as you have to multiply with larger numbers working your way through the equation. So the most efficient approach to clearing the denominator would be to choose to multiply by the lowest common multiple, the least common multiple of 2 and 6, which is in fact 6. Now remember, you can multiply an equation by whatever you want so long as you do it equally on both sides. If you put up a fence at this point, you could choose to multiply the expression on the right by 6, as well as the entire expression on the left. Technically that would require you to group the expression on the left and put a 6 out in front and then distribute, but I'm going to suggest that so long as you remember that you have to multiply the entire expression on the left, or increase the expression on the left by a factor of 6, and multiply all terms by 6, you don't have to show the distribution in the first step. Include the multiplication of 6 multiplied by both terms appropriately. You're not wrong at this point if you multiply 6 times x in the first term, and you get 6x divided by 2, and then you eventually simplify that to equal 3x. And you would also be correct if in the second term you multiplied 6 times x and got 6x in the numerator, and divided it by 6 appropriately and got 1x. But we always suggest that it's a good idea to simplify before you multiply. It leads to less steps. If you were to do that, 2 divides into itself once in the first term, and it divides into 6 3 times. And you're left with 3x divided by 1, which is just 3x. You could put it over 1, but it's not necessary because anything divided by 1 is just itself. In the second term, if you simplify before you multiply, 6 divides into itself once in the denominator and once in the numerator, and we're left with 1x divided by 1, which is just 1x, all equaling 12. Having chosen to multiply by the least common denominator, you have now canceled effectively out the denominators, and you have no more fractions to work with as you continue to solve this equation. In the expression on the left, if you collect like terms, 3x's plus 1 more x results in 4x's as the sum of 4x, and that's equal to 12. You could then undo multiplication with division and divide both expressions by 4, and you would get x equals 3. The same answer we got a moment ago. In the final step, it wouldn't have been wrong, and it might have even been more mathematically descriptive, to know that when you are dividing out the coefficient of 4, technically you're undoing multiplication with division, and division is the same as multiplying by the reciprocal. So you could have shown this as choosing to multiply both expressions by 1/4, the reciprocal of 4. That is a very clear way of indicating that we're using the multiplicative property of equality. You can multiply an equation by whatever you want, so long as you're equal on both sides. And the denominator means divide. 1/4 of 4x is just 1x, because the 4 divides to itself one time. And 1/4 of 12 is just 3, because the 4 divides to itself once and into 12 3 times. And once again showing that x equals 3. As the equations get a little more complex, such as number 4, this could be solved using methods that you had learned in 7th grade combined with some of the ones you're learning here in 8th. So it is entirely possible that you could choose to put up a fence and recognize that this is a little complex because you have variable expressions on both sides, or variable terms I should say, in both expressions. And you could choose to transfer the variable quantity, either of the variable quantities, by adding the opposite of their amount. So some students might say, Tooch, I'd like to add -2/3 x to both expressions, and that would be correct. You'd have to get a common denominator, you'd have to Subtract 2/3 from both expressions appropriately, or add negative 2/3 to x to both sides appropriately, and then you could solve a two-step equation along with that fractional, the remaining fractional coefficient as you work your way through. But I'm going to suggest that it becomes much more mathematically efficient to just choose to undo the fractional operation in the first step. Undoing the fractional operation in the first step would mean choosing to do the opposite of what a denominator does, divide, and multiply by the least common multiple of the denominators if you have more than one. So in this instance, you're supposed to recall that both 3 and 4 divide into 12. That would be the least common multiple. You wouldn't be wrong if you chose 24 or some other amount that 3 and 4 divide into, because you can multiply an equation by whatever you want, as long as you're equally on both sides. But I'm going to choose a least common denominator of 12. Choosing to multiply both expressions by 12 means that you're multiplying the entire relationship by 12, not just the fractional component, but also the numerical constant. So I'm going to multiply 2/3 by 12, 2/3 x by 12 in the expression on the left, as well as 2 by 12 in the expression on the left. In the expression on the right, I'll have to multiply 3/4 x by 12, as well as -1. That will effectively increase both expressions by 12. Now technically, you could have grouped each of the expressions and shown the multiplication of 12 on the outside of the parentheses amount, and then distributed in, but I'm trying to save a step here. Next, I would choose to simplify before I multiplied as I multiply the coefficient by the fractional quantities. So as I simplify the expression on the left, I'm going to choose to divide 3 into itself once and into 12 4 times, leaving me with 4 times 2x. 4 times 2x is just 8x. And technically you're supposed to say divided by 1, but that looks really awkward because anything divided by 1 is just itself. That's being increased by twice the value of 12, which is 24. And the expression on the right, once again I'm going to simplify before I multiply when I'm evaluating 12 times 3/4 x. 4 divides to itself once and divides to 12 3 times, and I'm left with 9x. And I'm subtracting from that 12 times 1, which is just 12. Having done that appropriately, choosing to multiply both expressions by the least common denominator of the fractional quantities, I've eliminated the fractions, and now I'm simply able to solve an equation as I normally would. I still recognize that there are variable quantities on both sides of the relationship, and I have to use an appropriate mathematical step to move or remove them. I typically suggest that you add the inverse of the variable term, the lower coefficient. In this case, that would be negative 8x. That would be 8x. And I would choose to subtract 8x's from both expressions. I like to show it as adding the opposite because it leads to less confusion when I'm dealing with a lot of negative signs, so it's a good habit to get into. In the expression on the left, positive 8x's plus negative 8x's, any amount plus its additive inverse equals 0. Or they simply cancel out. 8x minus 8x is 0, and I'm left with just 24. The expression on the right, 9x is less 8x is 1x, and I'm subtracting 12 from that term. It's now a two-step equation. I would begin by undoing addition and subtraction, so I'm going to choose to add 12 to both expressions. After undoing the subtraction with addition by adding 12 to both expressions, I'm left with 24 plus 12 is 36, and 1x is just 1x. There is no need to divide out the coefficient of 1 at this point because anything divided by 1 is just itself, so the answer is x equals 36. If I were to substitute that into the original relationship to check it, I would have to do 2/3 of 36, increase by 2, and determine if that's equal to 3/4 of 36, less 1. You can type each expression to calculator separately to determine their value. I'm going to choose not to do that because my calculator's been being a little funky, and I'm going to simplify them super quick without the use of the calculator. When I multiply 2/3 times 36, I can simplify before I multiply. 3 divides to itself once and into 36 12 times. When I double 12, I get 24, and when I increase 24 by 2, the result is 26. In the expression on the right, 4 divides to 36 9 times, and 3 times 9 is 27, and 27 less 1 is 26. The expressions are equivalent. When I substitute 36 in place of x, therefore 36 is the solution. If I had got something like 23 equals 48, that would not have been true, and x would not have been equal to 36. That would not have been the solution. I would have to have redone my work. In question number 7, this is one of the tougher ones we do throughout the unit, this style of question, where you're asked to solve for x and you're going to be forced to use many of the different techniques and mathematical rules and properties you learned throughout the unit. In question number 7, it's a good idea to get in the habit, whenever you're solving an equation, to try and clear parentheses or distribute right away if there's any distribution to be performed. So in the expression on the left, you notice that in the numerator of the fractional term, you could quadruple the quantity x less 2. I always like to draw distribution arrows when I'm showing that multiplication. That way I don't forget to perform either of the appropriate multiplications. When I quadruple x less 2, the product should be 4x less 8. And I still have to divide that by 5. When I increase it by 7, the entire relationship should equal 4x less 6 divided by 2. Once you've cleared parentheses, the next hurdle that we often want to jump over is managing any fractions that are within the relationship. And we have two. We have a fraction with a denominator of 5 and a denominator of 2. There are some students who will immediately multiply both expressions by 5, which is a little bit cumbersome because you're going to eventually have to divide by 2 or manage the division of 2. And then you'd have to multiply by 2 as well. It's more efficient to understand that since we want to clear a denominator of both 5 and 2, that we could multiply by the least common multiple, or any multiple of 5 and 2. The least common multiple would be the most efficient method because the multiplications would be a little less complex and the numbers wouldn't be as high. So although you could multiply by 20 and you could multiply by 30 and any amount that 5 and 2 divide into, it's easiest to multiply by 10. If you choose to multiply both expressions by 10, which you're allowed to do because you can multiply an equation by whatever you want so long as you do it equally on both sides, it would require that you multiply not only the fractional term in the expression on the left by 10, but also the numerical constant of 7. In this instance, it might be easiest to start in the right-hand side. Now technically you could distribute 10 into the numerator and get 40x less 60 and divide by 2, but it's often easiest to simplify before you multiply. 2 divides 2 itself once and into 10 5 times. Then you could distribute 5 into the numerator and the result would be 20x less 30. Technically divided by 1, but there's no need to show that because anything divided by 1 is just itself. In the expression on the left, 5 divides to itself once and into 10 2 times when we do 10 times the fractional quantity, and you choose to simplify before you multiply, and then you have to distribute the 2 into the numerator of the fraction. When you double 4x less 8, the result is 8x less 16. Technically over 1, but once again no need to show it because anything divided by 1 is itself. And the most common error students make is they forget that when they're taking 10 times the value of the expression on the left, they must also take 10 times 7. That's often left out. Students often just write 7 here, but you must have 70. Now that you have cleared parentheses and cleared the denominators of the fractional quantities throughout the relationship, you could go ahead and follow the steps to continue to solve the equation by collecting like terms. I want to add negative 16 and 70 together in the expression on the left, or do 70 less 16. Remember, subtraction is the same as adding the opposite, so 70 less 16 is the same as 70 plus negative 16, and I'm left with 8x plus 54, and that equals 20x plus 30. At this point, I hope that you recognize that this is a little awkward because there are variables in both expressions, so I want to move or remove a variable quantity from one of the expressions, and most efficiently that's done by adding negative 8x to both expressions, subtracting 8x from both sides. You can add whatever you want to an equation so long as you do it equally on both sides. The relationship will not change, it will just look different. You're left with 54 equals 12x less 30. Now you're solving a two-step equation. It's a good idea to undo addition and subtraction first. The result is that 84 will now equal 12x after you've added 30 to both expressions. And then you want to undo multiplication with division. We don't want the value 12x's, we want the value just 1. So we'll divide both expressions by 12. When we divide both expressions by 12, we're left with 12 dividing into itself one time in the expression on the right, equaling 1x, and the expression on the left, 84 divided by 12 is 7. We could check our work, but because we're a little short on time, I'm going to show you that that should work. And I'm going to hope that you understood all the concepts involved. So we solved more complex fractional relationships today, and we did that by understanding that it would be a good idea, rather than using the skills from 7th and 8th grade and trying to get common denominators and then following appropriate algebraic processes and subtracting or adding the fractions and then working our way through the equation. It's just a lot easier to get rid of the fractions as soon as we're able to. I suggest that it's a good idea to distribute whenever you're able to prior to trying to get rid of the fractions, because that leads to a little less confusion. It wouldn't have been wrong if students chose to immediately try and multiply both expressions by 10, the least common denominator, but there is some confusion that happens when you have 10 times 4 times the quantity of x less 2 divided by 5. It gets a little bit difficult to follow all the multiplications that happen. But if you do choose to clear the denominator in the first few steps, it's going to result in you having to not work with fractions as you continue to solve the rest of the more complicated relationship. So as we solve equations moving forward, it's a good idea to clear parentheses right away, then to clear any fractional quantities using the multiplicative property of equality. I would simplify the expressions on either side of the equation, or as some people like to say, collect like terms. Then you can usually transfer a variable quantity using the additive property of equality and solve a two-step equation appropriately. This was the lesson on solving more complex fractional equations by clearing the denominator. I hope that you understand the concepts embedded as best as possible.